Greetings, physicists. This video will be about how to deal with standing waves on strings. So, let's look at this thing about spiders here, because they sit on strings all the time. We have the not tensile strength, but linear density here of a spider web. And we have the average tension in a spider's web. So we've got a little, let's see if I can draw a spider here. 1, 2, 3, 4, 5, 6, 7, 8. There we go. And he's sitting on all of this web. Right, this is how spider webs go. And somewhere over here, some bug lands. That's a bug, right? Sure. Okay. And that insect happens to be 30 centimeters away down whatever piece of string that is, piece of webbing. How long before the spider figures this out? You can guess it's probably not going to be very long, so let's go ahead and solve this up. So we're looking for a time. What have we got? We've got a tension. We've got a linear density, a mu. Mu is equal to mass per unit length. And in this case, we don't even need to worry about what the mass and length are. We know the ratio, which is 1 times 10 to the minus 5. So, well, we know the velocity here. The velocity of waves that travel through strings is equal to the square root of the tension divided by the linear density. Okay. And we have those things, but we're not looking for velocity, we're looking for time. So we need to substitute something for velocity. Well, remember velocity, if we're saying this string has got a constant velocity, then it would be a delta x over a delta time. So if I solve for delta time, I get delta x over velocity. Well, it might be easier to just plug delta x over t for v. No, this way. There you go. All right, this way. So if I just take this and plug it in here, I'm going to get delta x over delta time equal to square root of tension over mu. Solving for delta time, so I'll multiply delta time this side and divide it over here, or get rid of it. And then I'm going to divide by this, which essentially will multiply by the inverse. So I'm going to get delta x on this side times the square root of mu over tension equal to delta time. And I should have all of those things. Now I'm going to change delta x into from centimeters to meters, so 0.30 meters. And the square root of mu was 1 times 10 to the minus 5, 1.0 10 to the minus 5. Boy, my penmanship is on point today. 5, that's kilograms per meter. And on bottom I should have a mu. No, that's wrong. The bottom should be a tension. Should be a 0.40. And a newton is a kilogram meters per second squared. Okay. Why do I think my units are not going to cancel here? Well, let's see what happens. Anyhow, if I do, well, let's put the numbers in before I start second guessing myself. I should have 0.3 times the square root of 10 to the negative 5 divided by 0.4. Okay, the answer I get is something like 0.0015. Now here's where I'm second guessing. So I have kilograms that cancel and meters that cancel, and second squared square root should give me seconds. This is bugging me. Because this is the right answer. It's definitely 0.0015 seconds, which if I move the decimal 1, 2, 3 times, I get 1.5 milliseconds. The one thing that is bothering me is why isn't my unit canceling? All right. Well, I may just have to leave that and come back to it later. All right. Let's move on. 2.5 meter long string vibrates as 100 hertz with nodes there and there. Okay. So this is a standing wave on a string. From one end, and at no points between those two, which harmonic is this? Oh, a bunch of questions. Okay, so let's draw this. So I have a string vibrating. I'll draw the wave pattern later, but right now what I'm interested in is that the whole length of the string from there to there is 2.5 meters, and then here at 1 meter and here at 1.5 meters, those are two consecutive nodes. Now there's a problem with that, because when strings vibrate, the ends are also nodes, like this, and this distance is 1, and this distance is 1, but this distance is only a half. And so there's got to be more nodes here. We don't have unequal wavelengths between successive waves on strings. That's not a thing, at least not standing waves anyway. Well, one thing they tell us is there are no points in between those two nodes. So that is essentially going to be the distance between all nodes on this string. So between 1 and 0, there's going to be a 0.5 node. Between 1.5 and 2.5, there's going to be a 2.0 node. So that's 2.5 here, and that's 0 here. There's no other way to do this. All right, so when you draw this, okay, so that's the wave pattern, and it would repeat on the other side as well, but I'm just going to draw this because it's easier for me. So that's one wave right there. That's two waves and a half. Sweet. So the first question, which harmonic is this? I do it like so. If I had the fundamental harmonic, I should have two nodes. If I go to the second harmonic, I should have three nodes. So every time I go up a harmonic, I'm going up a node. So if I had 2, and then how many in between? 3, 4, 5, 6. So there's a total of 6, and it's basically n minus 1 is your harmonic, right? Because we had 2 at the first harmonic. So this is the fifth harmonic. Fifth harmonic. Okay. Let's look again. What is the string's fundamental frequency? This is the fifth harmonic, and it's vibrating at 100 hertz. And so essentially you can do it like this. The fifth harmonic is 5 times the first harmonic, because every time you go up a harmonic, you go up by the first harmonic. So 5x equals 100 hertz. So x is going to be 20. And that should make sense. If I'm 20, second harmonic is 40, then 60, then 80, then 100. So that should work for us. So the fundamental harmonic N1, or actually I'll go ahead and say, it says what is the fundamental frequency, so we would say the fundamental frequency F1 is 20 hertz. What is the speed of waves traveling on the string? Let's see here. Well, right now, and I think it means this one, not the fundamental harmonic, but the fifth harmonic here. What is the speed of these waves? So our speed equation is v equals f lambda. We have a frequency. The frequency at the fifth harmonic is 100 hertz. They told us so. So now we need a lambda. So if I'm looking at this, a lambda is between any two nodes. So like from 1 to 2. Sorry, between it would be between any two peaks or any two troughs, or if you skip a node in between. So there's that. So you have to complete the wave once. So this is a 1 meter wave. So lambda equals 1 meter. Okay, so this is super easy math. It would be 1.00 because that's how many they gave us. So V equals frequency of 100 times 1.0 would be a 100 meter per second wave. Pretty straightforward. And yes, I did have, this is a 3 sig fig problem. So when I write that, I can put a little bar there to say, yes, that is how precise I am. Otherwise, this looks like it could be a 1 sig fig problem. So just tangent here to talk about sig figs. Sometimes when people write 100 and they want you to know that both zeros are significant, they will include the period, but they won't put any zeros after the period. That's one way to do it. This is one way to do it. And the other way is to go 1.00 times 10 squared meters per second. Just put it in scientific notation, and then it's very obvious that that zero is significant. I would say that this is the most correct answer, but it's also the most tedious to write. On a test, you should get credit for this. Moving on. Guitars. Yes, stringed instruments. Always going to include one of these. Guitar player plucks the string, then he presses a fret. So if you have a guitar, here's a guitar, right, like that. It's got a little bit here, little pegs. Frets. And we get 1, 2, I'm not going to have enough room for all of these strings. Anyway, let's just pretend that one of these strings, so the string is this long. Then he holds his finger, right? He holds the finger here, so the string is now only this long. So he holds down that fret to make the string shorter. What happens to the frequency? Do we get lower or do we get higher? Well, the thing he's not changing is the tension. That's going to be the same. So the velocity is going to be the same. So in V equals F lambda, he's not changing the speed of the wave on that string. What he is changing is the length of the string, the lambda. So the wavelength now, the wavelength used to be something like this, depending on which harmonic he's in. Actually, I think we probably assume that unless he's going for overtones, he's going for the fundamental harmonic every time he plucks the string. So the original wave was like this, and the new wave is only like that. So we've shortened the wavelength. Well, if the speed is going to stay the same, if the lambda goes down, the frequency goes up. Those are inversely proportional to each other. So we would get a higher frequency because we had a shorter wavelength. Okay, next question. The frequency of one string is too low. How can the tension be adjusted? All right, well, we need our tension equation here. So for a string on a wave, we have that the velocity on that string would be equal to the square root of the tension divided by the linear density. And we will assume that the linear density does not change much when you tighten it for these strings. So velocity and tension are directly proportional to each other. So we could also do like this. So if I put these together, I can say that the frequency times lambda, that's the velocity, is equal to square root of tension over mu. So tension and frequency should be directly proportional. So a higher tension should lead to a higher frequency if we keep the length of the string the same, because we're not really changing. The length of the string is just this long. That base length is not changing. So if I increase the tension, I should get a higher frequency, and if I decrease the tension, I should have a lower frequency. What is it asking for? The frequency is too low, meaning I have to make it higher, so I'm going to have to raise the tension to raise the frequency. So I tighten the string. Okay, so that's how to solve string and resonance problems.